Hello, geometry. This lesson is entitled the Polygon Angle Sum Theorem. First, let's go over some vocab. What is a polygon? That's a great place to start. Well, a polygon is three or more sided enclosed figure that only intersects at its endpoints. So the sides can't cross over each other. They only meet at their endpoints. And again, also the key thing is that it is an enclosed figure. Okay? Three or more sides, enclosed figure. So, the question is now, what is a convex polygon? A convex polygon is a polygon in which no line segment between 2 points on the boundary ever goes outside the polygon. And again, we will get to what that looks like right after we finish our vocab here. But again, convex polygon, you cannot create a line segment between 2 points on the polygon in which that line segment would be outside the shape. Okay? So, the opposite would be concave. So a concave polygon is a polygon in which a line segment between 2 points on the boundary does go outside the polygon. Okay? So again, one says that a polygon, the line segment cannot be outside. The other says it can be outside. So convex cannot. Concave, you can have a segment that goes on the outside. Okay. Next we have regular polygon. Okay? A regular polygon is a polygon that is both equilateral and equiangular. So the angles, the interior angles on the sides will be all the same degree measure, and the length of each side of the polygon will be the same measure in length. So it's both equiangular and equilateral. Okay, now let's go back to the concave convex. Alright, so classify each polygon as concave or convex. So again, convex means you cannot create a line segment that goes outside the polygon, whereas concave you can. So this first one, here we have the red shape. Notice there's no segment when you attach. So let's take this point right here. If I were to go across to any of these endpoints, okay, none of those segments are going to be outside of the shape. Therefore, this first one is convex, okay, because you cannot create a line segment on the outside. The second one, the blue one, though, we see here that we actually can connect a segment on the outside of the polygon from one point to another. So in this case, this would be the opposite of convex, which is concave. Okay. Now this last one, also we see that it's like the first one. It's convex, but if I were to actually put a couple markings here, okay. Now again, with the markings, as we learned before, that if it's the same amount of markings, that means they're all congruent. So in this case, not only is it convex, but it's also regular. It's a regular convex polygon. Okay? So again, we need to know the difference between convex and concave. This next example says, name the polygon in two different ways. Notice it doesn't say classify. Okay? Classify would be kind of more of a description. So convex, concave, or naming it by, or classifying it by the number of sides. But here, in this case, it says name the polygon. We actually want to give this polygon a name. Well, when it comes to naming a polygon, all you have to do is start at one vertex and either work clockwise or counterclockwise all the way around. It doesn't matter what order, it doesn't matter which direction, as long as you stay in order. So if I were to start with point B, I can work clockwise. So the way I would name this polygon, I would say B, D, H, K, M, G. That is one way of naming it. Again, I started at B and worked clockwise. And again, you can start at any point. So to name it another way, I can start at G and go counterclockwise. So the name of it would be G, M, K, H, D, B. Okay? So the one thing you don't want to do is wherever you start, make sure you don't skip any letters. You can't just throw the letters there randomly. You have to go in order, clockwise or counterclockwise. Okay, so that's how you name a polygon. In this case, we did it in two different ways. Alright, now let's move on here. Here it says 3 polygons are pictured at right. Name each polygon, their sides, and their angles. So it looks like 2, but we have to remember that the shape as a whole is a polygon itself. So that's why there's 3. So let's start with the 2 smaller ones. So let's start with this one first here, this triangle. Okay, we need to name that polygon. Again, you can start with any letter and work your way around. We only have 3 letters, so limited options. So we'll say A, B, E. So that's for the blue one. Now it says name their sides. It's a triangle, so we're going to name 3 sides. So we have side AB, and it does end. So they are segments, not lines. We have AB, BE, and EA. And we need to name their angles. Again, triangle, 3 angles. Now we can call the first one angle A. Okay, we can call this angle right here angle A. But please be careful when it comes to labeling the other 2 angles, because we can't call the one at top angle B, because at the vertex B, there's multiple angles being created. So in that case, we have to use 3 letters. So B is the vertex, so that has to be our middle letter. So we would say angle A, B, E. You could have said EBA also. And so for our third one, we would say angle BEA, because same problem down at the vertex of E. There's multiple angles being formed at E, so you can't use one letter. A, at angle A, or a vertex A, notice there's only one angle formed, so that's when you can use only one letter. Okay, now let's look at the one on the right. This is a quadrilateral, it's 4 sides. So, again, pick a letter. We'll go B, C, D, E. Again, don't cross over. You have to stay in order, either clockwise or counterclockwise. Now again, it's quadrilateral, so we're going to name 4 sides. So we have BC, we have CD, DE, and EB. That last one is a B. Just bad handwriting. Now our 4 angles, again, when we name this one up top, we can't use one letter because there's multiple angles at B. So we would say angle EBC, B being our middle letter. Now when we talk about this one right here, at C we actually can use one letter because there's only one angle being formed. So also angle D, and lastly at the vertex E we have to use 3 letters, so we would say angle DEB. Okay? I know this is kind of a long problem, but we have to name all 3. So our third one that we're going to do is the shape as a whole. Okay? So the entire shape. So we don't care about that middle segment BE. So if we were to name this, we would say A, B, C, D, E. Now the sides. Now notice there's 1, 2, 3, 4, 5 sides. So when you are naming all the sides, you got to have all 5. So we have AB, BC, CD, DE, and then back to A, so EA. Now naming the angles, we're kind of running out of space here. We have angle A. We can also use angle C for 1 letter, angle D for 1 letter, but notice that B and E, again, you have to use 3. But you have to watch out with 3. Since we're trying to name the whole angle, we can't say ABE, we would say angle ABC, from A to B to C. And lastly, angle DEA, from D to E to A. Okay? So again, naming polygons, you use their vertices, sides, 2 letters with that segment above it, no arrows, and angles, either 1 letter or 3, depending on how many angles are formed at that vertex. Okay. Now, classifying by the number of sides. How do you classify polygons by the number of sides? Each one has a name. Well, most have a name. So starting from 3 to 12, we're going to name specific names for each polygon. Everyone's really familiar with the 3-sided polygon. That one is called a triangle. Next, 4-sided polygon, we have a quadrilateral. It's tempting to put rectangle or square, but those are types of quadrilaterals. A general 4-sided polygon is called a quadrilateral. 5-sided is a pentagon. 6-sided, a hexagon. 7-sided, a heptagon. 8-sided, an octagon. 9-sided is a nonagon. 10 sides is called a decagon. Now 11, feel bad for 11. 11 didn't get a name. All these have specific names for them. You know, the pentagon, hexagon, heptagon, octagon. But 11, whoever came up with these names decided that they were going to be lazy and didn't come up with the one. So we call the 11-sided polygon an 11gon. Apparently, we ran out of ideas. So we have that as an 11gon. But 12 apparently has its own name as well. So that's why 11 got left out. A 12-sided polygon is called a dodecagon. Do for 2, dec for 10. So 10 and 2 makes 12. A dodecagon. Now for everything past 12, we're going to call that whatever amount of sides, in this case n, we call it an n-gon. So that doesn't mean any number past 12 is called an n-gon. That means if we were talking about 13, we'd say 13-gon. A 14-sided polygon would be a 14-gon, and so on and so forth. So whatever n is, it's that number plus the little 3-letter phrase gon. So again, a 20-sided is a 20-gon. Okay, well, here let's go ahead and classify each polygon by its sides, and we're going to identify, wow, went right through the words. I meant to underline it. We're going to identify each as convex or concave. So in this case, we have 1, 2, I shouldn't mark it, I might confuse you with being congruent. We have 1, 2, 3, 4, 5, 6 sides, and it is convex. So we would call this a convex hexagon. Okay? So again, there's no segment you can create that's going to be on the outside of the polygon, and it's 6-sided, so therefore it's a convex hexagon. Now this last example, we have 1, 2, 3, 4, 5, 6, 7, 8. So in this case it's an octagon, but since we can connect on the outside, it's going to be concave. So again, this is a concave octagon. Okay? So that's how you classify by convex or concave, but also classify by the number of sides. Alright. Now we're going to see if we can come up with a formula here. Here it says use diagonals from one vertex to construct triangles within the polygons. So for this first one, all we can do really is cross from one vertex to the other, if we're going to stick from one vertex. Because notice going to the others is actually along the outside of the polygon. So here it says the number of sides. We had 4 total for this first one. Okay? How many triangles were formed when we had a 4-sided polygon? Well, we created 2 triangles by, again, drawing this segment going across. Now, the sum of the interior angle measures. The thing about this is we learned that there's 180 degrees in every triangle for an interior angles. So when you add those together, we get 360 degrees for, that's poorly written, we have 360 degrees for a quadrilateral. Now this next one is a pentagon, so 5 sides. But if I were to connect, I can actually have use 2 segments going on the inside to create, in this case, 3 triangles. Now again, if they're each 180, I have 1, 2, 3 triangles. So if I multiply that by 180, I get 540. Now for our last one here, if I start from this vertex, cut across at the top, and then work our way down, creating diagonals. Now here, if you count the sides, you'll notice that there are 6 sides. We just created 4 triangles. So again, when you take that 4 triangles, times it by 180, we get 720 degrees. Now the question is there a correlation here with the number of sides and the number of triangles? And then finally the degree measure. Keep in mind that each triangle is 180 degrees. Okay? Well, they have come up with a formula which we can deduce here. Notice there's 4 sides minus 2 gives us number of triangles. 5 sides minus 2 gives us the number of triangles. 6 sides minus 2 gives us the number of triangles. And then we multiply those by 180 to find the sum of the interior angle measures. So the formula is n minus 2 times 180 will give us the sum of the angles inside the polygon, n being the number of sides of the polygon. Okay? So here it says find the sum of the measures of the angles of a 15-gon. Again, 15 playing the role of n. So what you do is you plug it right into the formula. So we have 15 minus 2 times 180. So therefore that gives us 13, 15 minus 2, times 180 is equal to 2,340 degrees. So if you were to have it at 15 gon, whether it's, if you were to take a 15 gon, whether it's regular or not, if you were to add up all the measures of the interior angles, you will get 2,340 degrees. Now here it says the sum of the measures of the angles of a given polygon is 720. How many sides does a polygon have? Now we noticed from our table before, we already know that it's 6. But how can we use this formula up here to prove that? Well, again, in this case, we don't know the number of sides. Well, we're going to act like we don't know. So we have n minus 2 times 180 is equal to 720, because we do know that the sum of the angles in this problem is 720. So we're just going to do proper steps in math, some algebra here, to get n by itself. So first, since it's multiplication in between these 2 parentheses, we can go ahead and divide that 180. Okay? Now if you do that, you're left with, on the left, n minus 2. 720 divided by 180 is 4. And then we would get n by itself by adding 2. So we get n is equal to 6. Therefore, we know we're dealing with a hexagon because it is a 6-sided polygon. Okay? Find the measurement angle y in this pentagon. So we have to find this angle measure right here. Now, again, we know 4 of the 5 measures of this pentagon. So the first thing we actually want to do is figure out what is the total degree measure of a pentagon. So we plug in 5 minus 2 times 180 will give us the total amount of degree measures. So that's 3 times 180, which is 540. So that's what all 5 will add up to. Well, we know that this is 90 because of the measurements, because of the markings. We know that's 90, and we know this is 90. So just those 3 alone, we get 270. We also have that 135 there. Now, if we were to add those up, that would give us 405. Those are the 4 angles that we know. We don't know the measurement angle y yet. So we could set it up that the 4 angles plus the measurement of angle y is equal to 540. So to get measurement of angle y by itself, we would subtract 405 from both sides, and you'd be left with 135 degrees. Now, I know you can look at this and say, well, it looks symmetrical and just a mirror image, so therefore, can't we just assume that these opposite angles are congruent? To an extent you can, but at the same time, it's not going to work out all nice and neat where it's going to be symmetrical like this every time. So you still want to go through the process of finding the total degree measures, and then subtracting the ones that you know, and that'll leave you with what you're looking for. Okay? Alright. Now let's move on. Polygon angle sum theorem. Okay, that's what we're dealing with here. You can draw exterior angles at any vertex of a polygon. What is the sum of the exterior angles? Now this is something interesting because the interior angles we've noticed have been changing for every degree measure. But here, if we look at this triangle, again what happens is if we extend this past, we get an angle that gets created on the outside. Okay? In this case we're going to have 3, because it's a triangle, there will be 3 exterior angles. But when you add all these 3 together, you're going to get 360 degrees. Okay, for the triangle, the exterior, sum of the exterior is 360. But notice, if you do the same thing over here, again, we have 4 exterior angles formed. If you add 115 plus 75 plus 99 plus 71, that also is 360. And same thing over here, finally. This will also be 360 when you add up all of the exterior angles. So, I mean, if we did 3 different examples with 3 different polygons of different amount of sides, we got 360 on every time. We can conclude that the sum of the exterior angles will always be 360 for whatever polygon it may be. Okay? This is just an example to give us a pentagon, but again, it works for any polygon. The sum of the exterior angles of a polygon, one at each vertex, is 360 degrees. Well, this comes to our last example. This game board at the right has the shape of a regular hexagon. It is packaged in a rectangular box outlined beneath. The box uses 4 right triangles made of foam in its 4 corners. Okay, they want to keep this board game nice and snug, so they put these foam triangles right here. Okay. Now it says find measurement of angle 1 in each foam triangle. Now the key word to this problem is regular. For a regular hexagon, that means all the sides are congruent, which also means all the angles are going to be congruent to each other. So, therefore, if it's a hexagon, we want to find the total amount of degrees. So we do 6 minus 2 times 180, and this becomes a 4. So 4 times 180 is 720 degrees. Now that's the sum total of the interior angles. Now if they're all the same, if it's regular, we can actually divide by 6 to come up with one angle. So with one interior angle, to be more specific. So when you divide that by 6, you get 120 degrees. So again, what does that 120 degrees represent? Well, that 120 is this degree measure right here. Again, the interior angle. But we're looking for the exterior angle, correct? Well, we notice that these are supplementary, okay? So therefore, these two need to add up to 180, so that would leave the measurement angle 1 is equal to 60 degrees. Now, that was kind of the longer way of finding that exterior angle. But remember, what we just got taught here is that the sum of the exterior angles is 360. So another way you could have done this, instead of finding one interior angle, since we know that angle 1 is an exterior angle, so this is an exterior angle, for a hexagon there's going to be 6 of those. So we take 360, we divide that by 6 exterior angles. Notice we get the same answer. We get 60 degrees. Okay? So, there's two ways of doing it. One requires a lot less work. If you're looking for an exterior angle, just divide it from 360 and that will give you that 1 if it is a regular polygon. Okay? So good luck with that, and please ask any questions that you may have if you are confused by any of this. Good luck.